Massive stones fit together so perfectly that not even a blade of grass can slip between them. This is the staggering precision of ancient engineering, a global mystery pointing to technology lost to time. By the end of this journey, you will see human history in a completely new light. How did civilizations without modern machinery cut and shape granite with microscopic accuracy? What forgotten knowledge allowed them to soften stone like clay? The answers challenge everything we think we know about the past. What does it say about our own civilization that such incredible feats were achieved so long ago? Stand before the colossal walls of Sacsayhuaman in Peru, and you are met with a sight that defies simple explanation. These are not mere blocks of stone. They are a monumental jigsaw puzzle, each piece a granite giant weighing dozens of tons, locked together with seams so tight they seem to have been fused. You could spend a lifetime trying to slide a razor blade between them and fail. This is not rustic construction. This is engineering on a level that challenges our modern arrogance. And this mystery does not stand alone. From the impossible angles of the Egyptian pyramids to the interlocking stone tombs of Okinawa, Japan, a global pattern emerges. Scattered across continents and oceans, separated by thousands of years, our ancestors left behind a silent, stone testimony to a knowledge we can scarcely comprehend. Mainstream archaeology tells us these were achieved with copper chisels, stone hammers, and sheer manpower. Yet when modern engineers and stonemasons examine these sites, they are left baffled. The precision is too perfect, the tolerance is too fine. The technological gap between the accepted historical narrative and the physical evidence is a chasm. This forces a profound and unsettling question. What forgotten art, what lost science, allowed these builders to engineer stone with what seems like atomic-level precision? The clues are embedded in the stone itself, waiting to be read. That first evidence is written in stone itself, a tactile marvel you can still experience today. Run your fingers along the joints of the granite blocks at an Egyptian temple like the Osirian, and you feel nothing. No ridge, no gap, no unevenness. Your skin registers a seamless, cold surface, even though you are touching two separate stones, each one weighing as much as a small whale. There are no tool marks, no chisel scars, no mortar to fill the voids. The stones simply meet, conforming to one another with a perfection that modern machinery would struggle to replicate. This is not just a tight fit. It is a fusion. The surfaces are so precisely matched that they exclude even air and moisture, creating a bond that has endured for millennia. The stones are not just stacked, they are interlocked in complex, multi-angled shapes. At sites like Ollantaytambo in Peru, you see blocks with more than a dozen distinct angles and protrusions, all fitting perfectly into their neighbors like a three-dimensional puzzle. This geometric complexity is staggering. Think of trying to carve a single, giant piece of granite with 20 unique faces, and then carving the empty space next to it to be its perfect mirror image, all without computer-guided precision. The sheer weight of these blocks adds another layer of impossibility. We are not talking about lightweight bricks. These are masses of granite and basalt, some exceeding 300 tons. The process of simply moving them into position without shattering the razor-sharp corners is a monumental task in itself. Yet the joints show no signs of the crushing or spalling you would expect from brute force methods. The stone seems to have been placed with a gentle, deliberate finality. How could this be achieved? The absence of weathering within the joints themselves is a critical clue. While the outer faces of the stones are worn by wind and rain, the interfaces between them remain pristine. This suggests they were never truly separate surfaces exposed to the elements. but were joined in a way that created a single, continuous mass. The global consistency of this technique points away from isolated genius and toward a shared, forgotten understanding of the material. The stones at the Osirian in Egypt and the walls of Ollantaytambo in Peru, separated by an ocean, speak the same silent language of impossible precision. This was not primitive hammer and chisel work. This was something else entirely, a method that treated stone not as a rigid solid to be broken, but as a material that could be persuaded, softened, or even molded into place. The stone itself bears a second, even more perplexing kind of evidence, one that suggests a radical and almost alchemical transformation. In scattered ruins from the hill forts of Scotland to the highlands of Peru, we find stone surfaces that appear to have been melted. These are not merely cut and fitted blocks, but rocks that have been vitrified, their outer layers fused into a glassy, obsidian-like crust. It looks as if a colossal and precise heat source washed over the granite, turning it momentarily liquid before it cooled into this strange, solidified glaze. To achieve this, the stone had to be heated to a temperature exceeding 2,000 degrees Fahrenheit, a heat so intense it would liquefy modern steel. Yet there are no signs of sustained volcanic activity or lightning strikes at these locations. The vitrification is often localized to the upper portions of walls, as if the heat was applied deliberately from above. Materials scientists who have studied these sites are unanimous in their bafflement. Creating such a vitrified layer on granite is not a simple matter of throwing wood on a fire. It requires a sustained, focused, and incredibly high-temperature source, something far beyond a simple bonfire. The process also demands a sophisticated understanding of how different minerals within the granite melt at different rates, a knowledge of chemistry that seems impossible for so-called primitive cultures. So how could such heat be generated and, more importantly, controlled? The energy required is monumental. We are forced to consider possibilities that sound like they belong in a science laboratory, not an ancient construction site. Could there have been a method to focus sunlight, using vast arrays of polished mirrors to create a cutting and welding torch of solar energy? Or perhaps they harnessed chemical reactions, combining specific minerals to create a thermite-like effect that produced a brief, searing inferno. Some researchers even point to the potential use of directed sound or plasma, forms of energy we are only just beginning to master today. The presence of vitrified stone is not a random act of nature. It is a deliberate signature, a ghost in the stone that points to a technology capable of manipulating the very atomic bonds of matter. This is not the work of brute force, but of a refined and terrifyingly advanced science. If they could make stone flow like water, then what other impossible feats were within their grasp? But the evidence does not stop at walls that seem fused or surfaces that appear melted. The third and perhaps most technically baffling piece of this puzzle lies in the cutting of the hardest stones on Earth. We are asked to believe that ancient artisans, armed with little more than copper tools and stone hammers, were able to work materials like granite, diorite, and quartzite. These are not soft limestones. Granite is an incredibly tough, crystalline rock, and diorite is even harder. Shaping them with primitive tools would be like trying to carve a diamond with a piece of chalk. Yet they did not just crudely shape them. They achieved a geometric precision that borders on the supernatural. Nowhere is this more evident than deep within the Serapeum of Saqqara in Egypt. Here, in a labyrinth of underground tunnels, rest dozens of colossal stone boxes, each one carved from a single, solid block of granite or basalt. They are often called sarcophagi, but their true purpose remains a mystery. What is not a mystery is the level of craftsmanship on display. The surfaces of these boxes are flawlessly flat and polished to a mirror finish. Their corners are perfect 90-degree angles inside and out. The real impossibility, however, lies on the inside. The interior corners are just as sharp and precise as the exterior. Modern stonemasons and engineers who examine these boxes are left speechless. How do you achieve a perfect internal corner in a block of solid granite? Even with today's most advanced computer-controlled machinery and diamond-tipped tools, this is an immensely difficult task. The tools we use have a radius. They cannot physically create a perfectly sharp internal corner. Yet, the boxes in the Serapeum have them. It is as if the stone was simply persuaded to take this shape. This same impossible precision is found in the sawing and drilling of these hard stones. At sites like the Giza Plateau, we find massive granite blocks with clean, straight cuts that run for many feet. The surfaces are so smooth they feel like glass. When a modern diamond-tipped saw cuts granite, it leaves behind distinctive, parallel scratch marks from the abrasive grit. These ancient surfaces show no such marks. The cut is simply there, pristine and unblemished. Even more telling are the drill holes found in granite and basalt. Core samples recovered from these sites show spiral grooves that descend into the stone, but the rate of the feed, the speed at which the drill advanced, is beyond what is possible with any known ancient technology. The grooves are too uniform, the progression too fast and steady. It suggests a drill that did not merely grind and abrade, but one that sliced through the granite with incredible force and efficiency, almost as if the stone was somehow softer during the process. Then there is the suggestion of lathe work. Some granite artifacts, like certain vases and bowls found in predynastic Egyptian sites, have a symmetry so perfect they appear to have been spun on a wheel. Their contours are flawless, their walls are uniformly thin, and the precision of their curves is something a modern machinist would be proud of. Yet, these objects are made of the same hard, brittle stone. To turn these on a lathe would require tools harder than the granite itself, and a power source to spin the multi-ton block at a stable, high speed. We have no evidence for such tools or such engines. The artifacts exist, but the technology to create them, according to our conventional history, does not. These are not one-off anomalies. They are a consistent, global signature of a method that treated the most stubborn materials in the world with an almost dismissive ease. The logical conclusion is as unsettling as it is inescapable. The builders of the deep past possessed a method for working stone that operated on a level we can scarcely comprehend, a process that rendered hard stone temporarily malleable, allowing it to be cut, shaped, and polished with a precision we would attribute to a machine shop. So what exactly was that miraculous process? The choice of granite was not an accident. It was a deliberate and almost defiant selection. Imagine an ancient engineer standing before a quarry, faced with a simple choice. On one hand, there is soft, workable limestone, a material that can be shaped with copper tools and patience. On the other, there is granite, a brutal, unyielding substance. They chose the granite every time. This decision is the first and most profound clue that we are not dealing with conventional methods. To understand why, we must look at the stone itself. Granite is not a simple rock. It is a complex amalgam of different minerals, primarily quartz, feldspar, and mica, all fused together in a crystalline matrix. Quartz is the key here, on the Mohs scale of hardness, which geologists use to rank minerals from 1, as soft as talc, to 10, as hard as diamond. Quartz sits at a 7. To scratch it, you need a material that is harder still. The copper chisels and stone hammers attributed to ancient builders have a hardness of only 3 or 4. Using a copper tool on granite is like trying to carve a steel beam with a stick of butter. the tool would simply deform and wear away long before it made a meaningful impression on the stone. This geological reality was understood across the globe. In Egypt, they sought out the pink granite of Aswan. In Peru, they used andesite, a stone with similar tough, crystalline properties. In the British Isles, they built with bluestone, another incredibly hard rock. This was not a local preference, it was a global pattern. The builders consistently sought out the most challenging materials available. Why would anyone do that? Why choose a rock that is exponentially more difficult to quarry, to shape, and to transport? The sheer logistics are mind-boggling. A single granite block from the Serapeum could weigh 70 tons. Moving it from the quarry, often hundreds of miles away, without the wheel or the pulley in some cases, would have been a Herculean task in itself. Then they had to lower it into a precise underground chamber. The risk of shattering such a valuable, labor-intensive object was immense. Yet they did it, and they did it with a precision that we struggle to match. This tells us something crucial. The difficulty of working the stone was not an obstacle for them. It was irrelevant. Their method of shaping was so advanced, so fundamentally different from chiseling and pounding, that the hardness of the material simply did not matter. Whether it was soft limestone or brutally hard granite, their process worked with the same effortless efficiency. The stone itself, with its crystalline defiance, is a silent witness to a technology that rendered our entire understanding of tool-making obsolete. If hardness was no object, then what incredible force were they wielding? Mainstream archaeology presents a familiar image. An expert stands before a granite block, a copper chisel in hand, patiently tapping with a stone hammer. Hours of dedicated labor later, a small, shallow scar mars the stone's surface. This demonstration is meant to reassure us, to show that the tools we have found in the archaeological record are indeed capable of the work. Yet this very demonstration reveals the core of the problem. The minuscule progress made over hours of work stands in stark contrast to the millions of cubic feet of granite shaped into perfect forms across ancient Egypt. The theory, while comforting, collapses under the sheer weight of the evidence. The primary explanation offered is a triad of simple tools: copper chisels for detail work, dolerite stone hammers for the rough quarrying, and abrasive sands used with water to slowly saw and grind the stone. These methods, in a laboratory setting over an indefinite time frame, can indeed alter granite, but the real world of construction operates under different rules. The Great Pyramid alone contains an estimated 2,300,000 stone blocks, many of them granite, quarried, shaped, and placed within a reigning period of just 20 years. When you run the numbers, the logistics become a nightmare. To complete the project on time, using only copper tools and abrasive sand, a block would need to be quarried, finished, and set into place every few minutes, day and night for 2 decades. This does not account for the perfect 90-degree angles, the mirror-smooth finishes, or the complete absence of tool marks on so many critical surfaces. Dissenting voices within the field of archaeology have long pointed out these glaring inconsistencies. They ask a simple, devastating question. Where are the tool marks? If millions of tons of granite were laboriously ground down with abrasive slurry, why do we not find the characteristic parallel scratch marks on every surface? Why are the interiors of the granite boxes in the Serapeum so flawlessly polished, a task nearly impossible with a hand-held sanding stone? The energy and time requirements are astronomical, far beyond what a Bronze Age society, even one as organized as ancient Egypt, could realistically muster. The conventional narrative asks us to believe that an entire civilization devoted generations to a single, back-breaking task using methods that are demonstrably inefficient. It asks us to ignore the physical evidence of melted and vitrified stone, the impossible internal corners, and the saw cuts that show no signs of abrasion. This is not a matter of missing evidence. It is a case of the existing evidence actively contradicting the accepted story. The chasm between what the theories propose and what the stones themselves proclaim is simply too wide to ignore. This critical failure of the mainstream explanation does not leave us with nothing. It creates an intellectual vacuum, an open space where more daring and revolutionary ideas can take root. The silence of these ancient sites is deceptive, for one of the most compelling theories suggests they were once filled with a profound and purposeful sound. Across disparate cultures, from the high Andes to the remote plateaus of Tibet, legends persist of a lost science that used harmonic resonance to manipulate matter. Tibetan monks speak of acoustic ceremonies where massive stones were levitated into place by teams blowing trumpets and chanting in precise unison. Inca oral traditions tell of builders who understood the spiritual songs of the rocks, using specific frequencies to make the stones lighter, even to the point of floating. These are not mere myths, but echoes of a principle that modern physics has only just begun to understand. Acoustic levitation is a real, observable phenomenon in laboratories today. Scientists use precisely tuned sound waves to create standing waves, nodes of pressure that can suspend small droplets of water or even solid particles in midair. The principle is one of energy and vibration. Every material has a natural resonant frequency, a specific pitch at which it vibrates most easily. Think of an opera singer shattering a crystal glass with her voice alone. She is not shouting randomly, she is matching the glass's inherent resonant frequency, transferring energy into it until it can no longer hold its structure. Now extrapolate that concept to a monumental scale. Could the builders have discovered the resonant frequency of granite itself? The hypothesis suggests that by using arrays of massive drums, horns, or even human voices chanting in perfect harmony, they could generate a powerful, focused acoustic field. This resonant energy would not necessarily make the stone float in the air like in a science fiction movie, though levitation of smaller blocks is theoretically possible. The more profound effect might have been on the stone's physical properties. Intense, specific sonic vibrations could have drastically reduced the effective weight of a block by counteracting gravity, or, even more radically, temporarily disrupted the atomic bonds within the crystalline structure of the granite. In this resonant state, the stone would become less rigid, more plastic, almost like a thick clay. This would explain everything: the flawless molding of multi-angled blocks, the seamless joints, the apparent lathe work on impossibly hard materials. The stone was not being cut, it was being persuaded. While we lack a time machine to prove this was used on ancient building sites, the circumstantial evidence is thought-provoking. Modern experiments have shown that certain resonant frequencies can indeed affect the flow and solidification of materials. More tellingly, the acoustic properties of sites like the Grand Gallery in the Great Pyramid have been studied for their unique ability to amplify and focus specific sound frequencies. Were these structures not just tombs or temples, but giant resonating chambers, sophisticated devices for harnessing the power of sound? The sonic hypothesis moves us from a paradigm of brute force to one of applied knowledge, a technology based on energy rather than mechanics. It suggests a civilization that had mastered the hidden vibrations of the world around them. If sound could soften stone and lighten colossal weights, what other forms of energy, now forgotten, might they have commanded? This line of inquiry leads us to the very edge of material science, to a possibility that seems drawn from the future rather than the past. Sound was not the only force they may have commanded. A more profound theory suggests the very planet itself was their power source. Envision Earth not as a static ball of rock, but as a living entity pulsing with subtle energies, a vast, invisible grid of power lines that ancient builders learned to tap. This is the concept of a global energy grid, a network of natural forces that could have provided the incredible energy required for their impossible feats of engineering. These are often called ley lines, hypothetical alignments that connect sacred sites and ancient monuments across staggering distances. Researchers in alternative history propose that these lines are not imaginary, but correspond to real geological features, such as deep crustal faults and underground water aquifers. Along these faults, the Earth generates weak electrical currents known as telluric energy, a constant flow of power from the planet's core. The builders, they argue, deliberately placed their most magnificent structures directly upon these energetic hotspots. The Great Pyramid of Giza sits at the exact center of Earth's landmass, a nexus point. Machu Picchu is built atop a major geological fault line. Stonehenge rests on a confluence of powerful underground water flows. This precise alignment cannot be mere coincidence. It suggests an advanced understanding of geomancy, the art of harnessing the Earth's spiritual and energetic forces. But how could this energy soften stone? The answer may lie in the stones themselves. Many of the hardest stones used in megalithic construction, particularly granite, are piezoelectric. This means that when you apply mechanical pressure or stress to them, they generate a small electrical charge. Now, imagine the immense pressure building up along a geological fault line. This constant tectonic stress would cause the granite in the area to become electrically active, creating a localized field of energy. Some theorists propose that the builders used specific crystals or other materials to focus this ambient Earth energy, much like a lens concentrates sunlight. By directing this concentrated energy field onto a block of granite, they could have excited the crystalline structure to its resonant frequency, or even temporarily weakened the atomic bonds holding the stone together, rendering it pliable. A quote from one researcher captures the essence of this idea, suggesting that these cultures saw the Earth as a conscious being and learned to work with its rhythms, not against them. Their construction was not an act of domination, but of harmonic collaboration. They built their temples as tuning forks for the planet, structures designed to resonate with and amplify the natural energies flowing beneath them. This holistic understanding of the planet's forces points to a science that was deeply interconnected with the natural world. If they could harness the very heartbeat of the Earth to mold stone, then their knowledge of chemistry, of the hidden properties of matter, must have been equally profound. What forgotten formulas or alchemical processes did they possess that allowed them to command the elements with such ease? Perhaps the most tangible answer lies not in sound or energy, but in a forgotten chemistry. The stone itself might have been softened, rendered temporarily pliable by a potent alchemical brew. This chemical softening theory suggests that ancient engineers possessed a plant-based or mineral-based solution capable of disaggregating the powerful silicate bonds that give granite its legendary strength. Imagine an artisan not with a hammer but with a brush, carefully applying a milky liquid to the surface of a granite block. Before their eyes, the unyielding stone would begin to sweat, its surface becoming tacky, then malleable like wet clay. In this softened state, the hardest rock on Earth could be molded into intricate shapes, pressed against a neighboring block to create a perfect seam, or even sculpted by hand. Once the desired form was achieved, a second chemical agent, an antidote, would be applied to reverse the process, returning the stone to its original, diamond-like hardness, leaving behind no trace of its temporary plasticity. This idea moves from pure speculation into the realm of plausible history when we consult the old stories. Spanish chroniclers in the Andes recorded Inca legends speaking of a mysterious plant whose juices, when mixed with other ingredients, could soften stone. The natives claimed their ancestors used it to make the stones fit together so perfectly. Similar tales exist in other parts of the world, from the jungles of Southeast Asia to the deserts of the Middle East, all hinting at a lost botanical knowledge, a secret of the natural world that has since faded from memory. What kind of natural compound could achieve such an incredible effect? Modern chemists who have investigated this possibility point to several candidates. Certain plants, like the dwarf rue or some species of algae, are known to produce organic acids such as oxalic acid, which can slowly etch and dissolve silicate minerals over long periods. But for a rapid, dramatic softening, the process would need to be far more aggressive. Some researchers propose a combination of chemicals that creates a powerful chelating agent. A chelator is a substance that binds to metal ions, effectively plucking them out of a mineral structure. Since the silicate network in granite is held together by metal ions like aluminum and iron, a strong enough chelator could theoretically cause the rock to lose its structural integrity, transforming from a solid crystal into a granular paste. The real challenge, however, is not just softening the stone but controlling the process perfectly. How would such an agent be applied? It could have been painted onto the surface, the stone then carved with simple wooden tools. Or perhaps blocks were submerged in large pits filled with a chemical solution, emerging ready to be molded. For the massive stones, a poultice might have been used, a thick paste applied only to the areas that needed shaping. The final and most crucial step was the neutralization. Without it, the stone would remain a crumbling mess. A neutralizing agent, perhaps a simple base like lime water or ammonia derived from animal urine, would lock the ions back into place, re-establishing the silicate bonds and hardening the stone for eternity. This would explain the complete absence of chemical residue on the ancient stones today. The evidence is not just in legends. There have been experimental attempts to replicate this effect. In the 1970s, a chemist named Davidovits proposed that the blocks of the Great Pyramid were not quarried at all, but were a form of ancient geopolymer, a type of man-made stone created by reacting limestone with a soda-based solution. While his theory for the pyramids is highly contested, his experiments demonstrated that creating a stone-like material from disaggregated rock is chemically possible. Other modern experimenters have used concentrated plant extracts to visibly soften the surface of granite samples, making them susceptible to marking with a fingernail. These are small-scale proofs of concept, far from explaining the quarrying of 70-ton boxes, but they validate the core principle that stone can be altered chemically. This theory provides a beautifully simple and tangible explanation. It does not require unknown energies or sonic technologies, just a profound, lost knowledge of botany and chemistry. It suggests the ancient master builders were not just engineers, but the world's first materials scientists, possessing a secret that allowed them to treat the most stubborn stone like potter's clay. A workshop from the deep past might not have echoed with the clang of hammers, but with the faint hum of an unknown power source. Envision a craftsman not straining with a copper saw, but guiding a sleek device that emits a concentrated beam of energy, slicing through a slab of granite as if it were soft wax. This is not science fiction, but a necessary theory to explain the evidence. The flawless, glassy surfaces and impossibly deep drill holes point toward tooling of an advanced nature, tools that have since vanished from the historical record. We must consider the possibility of diamond-tipped saws, their blades impregnated with microscopic fragments of the hardest natural material on Earth, capable of producing the clean, unblemished cuts we find. Or perhaps ultrasonic drills, vibrating at frequencies far beyond human hearing, pulverizing the stone at a microscopic level to create those perfect, deep boreholes with astonishing speed. Some researchers even look at the vitrified melted stone and see the signature of a plasma cutter, a technology that uses a superheated jet of ionized gas to slice through steel and could, theoretically, fuse the surface of granite as it cut. The core question becomes one of power. What energy source could have driven such tools, especially on the massive scale required for these projects? This is where the theories converge, suggesting these advanced tools were not powered by steam or combustion, but were plugged into the very planet, drawing upon the same telluric energy grid that may have softened the stone. The tool and the energy source would have been two parts of a single, sophisticated system. A quote from a modern mechanical engineer who examined granite artifacts from Giza sums up the dilemma perfectly. He stated that the feed rate and uniformity of the drill marks suggest a tool that applied immense, consistent pressure, a level of force and stability that would be difficult to achieve even with modern machinery, let alone with a bow-driven drill and abrasive sand. The evidence implies a technology that has been lost, a leap in engineering that our conventional timeline cannot accommodate. This leads to an even more startling sub-theory, the possibility of lost metals or superalloys. We assume ancient cultures had only copper, bronze, and iron. But what if they developed a material science that has left no trace for us to find? An alloy harder than any steel, perhaps even a form of tempered diamond itself. Such a material could account for the deep, precise incisions and the internal corners that defy our own manufacturing capabilities. The drill cores themselves are a silent testament to this mystery. The spiral grooves show a tool that removed material with an efficiency that seems to increase with depth, as if the drill bit became more effective the further it went, a phenomenon that contradicts the behavior of a simple, abrasive tipped tool. It suggests a cutting head that was self-renewing or that utilized a principle we no longer understand. These tooling theories push us to the very boundaries of accepted history, forcing us to contemplate a past where the line between myth and machine becomes dangerously blurred. If they possessed such devices, what catastrophic event or gradual decline could have led to the complete and total erasure of this knowledge from the face of the earth? Deep within every block of granite lies a hidden architecture, a perfect geometric order invisible to the naked eye. This is the realm of crystallography, the study of how atoms arrange themselves into repeating, three-dimensional patterns called crystals. Granite is not a chaotic jumble of minerals, it is a mosaic of interlocking crystals, each one a tiny fortress of atoms bound together in a rigid lattice. The strength of these atomic bonds and the angles at which they connect determine everything about the stone, its hardness, the way it fractures, and most importantly for our mystery, how it might be persuaded to yield. To manipulate stone with the precision we see, the builders would have needed to understand these invisible lines of force. They may have intuitively or deliberately exploited a crystal's cleavage plane. Think of the grain in a piece of wood, a natural line of weakness where it splits most easily. Every crystalline mineral has its own set of these internal planes, directions along which the atomic bonds are slightly weaker. A master stoneworker who knew how to tap along these precise angles could, in theory, split a massive block of granite as cleanly as a diamond cutter cleaves a gem with a series of calculated, light taps rather than brute force. This explains the impossibly smooth, flat surfaces on so many megalithic stones, surfaces that show no signs of the random, crushing impact you would expect from stone hammers. But what about the stones that appear molded, not split? This is where the atomic structure becomes the key to the entire mystery. A materials scientist would explain that to make a solid crystalline material pliable, you do not need to melt it into a puddle of lava. You only need to temporarily disrupt the powerful bonds holding its atomic lattice together. If you could find a way to input a very specific amount of energy, just enough to vibrate those bonds to their breaking point without completely destroying the crystal, the rock would enter a transient plastic state. In this softened condition, the granite could be pressed and shaped, its surface smoothed to a glassy finish by simple polishing tools, or even fused to a neighboring block under pressure. Once the energy source was removed, the atomic bonds would snap back into place, locking the stone into its new, impossibly precise form forever. This concept separates the materials the ancient builders favored from those they often ignored. Crystalline stones like granite and basalt have this defined atomic lattice, a regular structure that can be targeted and manipulated with resonant energy or chemistry. Amorphous materials like obsidian lack this repeating order. Their atoms are frozen in a chaotic, glass-like state. This makes obsidian incredibly sharp, but also unpredictable and difficult to shape with the same geometric precision. The builders consistently chose the crystalline stones, the ones with a hidden, orderly structure they knew how to command. This is not a trivial distinction. It points to a foundational knowledge of material science that seems to belong to a modern laboratory, not to a prehistoric quarry. How could an ancient civilization without electron microscopes or X-ray diffraction have acquired such an intimate understanding of atomic lattices and resonant frequencies? The answer may be one of patient, accumulated observation over millennia, a deep collaboration with the natural world that allowed them to listen to the subtle song of the stones and learn the secret of making them sing. The city of Cusco is cradled by walls that seem alive, stones that breathe and shift with the land itself. These are the iconic polygonal walls of the Inca, a masterpiece of engineering where massive, irregular blocks lock together in a seamless, undulating tapestry. No two stones are the same, each one a unique geometric shape with anywhere from 6 to a dozen perfectly fitted sides. They were assembled without a single drop of mortar, relying solely on the incredible precision of their cuts. Yet their most astonishing feature is not just how they fit together, but how they have endured. For centuries, violent earthquakes have shaken this region, toppling Spanish colonial cathedrals built directly atop these ancient foundations. The Inca walls, however, remain unshaken. The secret is in their brilliant design. Each massive block is slightly convex on its outer face. When the earth trembles, the stones do not rigidly resist the force, they dance. They vibrate and settle, the complex angles and slight inward lean allowing the entire structure to flex and then return to its original position, dissipating the seismic energy. It is a dynamic, living architecture that modern engineers can only marvel at. The puzzle deepens when we consider the raw material. These walls are not built from one single type of stone. The Incas used andesite, a volcanic rock nearly as hard as granite, and also a softer green diorite, often in the very same wall. This presents a profound mystery. How could they achieve the same flawless, complex fit on two stones with completely different hardness and mineral compositions, using only primitive stone hammers? The conventional explanation of pecking and grinding becomes almost comically inadequate. Furthermore, the surfaces of some of these stones hold a subtle clue. On certain blocks, particularly the andesite, there is a peculiar, almost rubber-like texture to the surface, a slight undulation that feels different from the sharp, crystalline fracture of a broken rock. Some researchers have pointed to this as potential evidence of a surface treatment, a sign that the outer skin of the stone was perhaps softened or made malleable, allowing it to be pressed and molded against its neighbor to achieve that legendary airtight seal. This idea is supported by the accounts of early Spanish chroniclers who recorded Inca legends of a plant-based juice that could soften stone. An archaeologist studying the site once noted that the joints are so perfect that it seems as if the stones were custom-fitted in a liquid state, a poetic description that points toward a radical, forgotten technology. The principles on display here are universal, a secret language of stone written in the high Andes. If the Inca possessed a method to make stone pliable, to fit these multi-ton puzzles with seismic resilience, then we must ask if the same secret was known to the master builders of another legendary site, a place where stone was engineered on a scale that still defies belief. Descending into the Serapeum of Saqqara is like stepping into a temple of impossible geometry. The air is still and heavy, and the silence is broken only by the weight of the mystery that surrounds you. Here, resting in shadowy niches, are 24 colossal boxes, each one carved from a single, solid piece of granite or basalt. They are immense, some weighing over 70 tons, the equivalent of a fully loaded semi-truck. Officially, they are labeled as sarcophagi meant to hold the sacred Apis bulls. Yet when the great explorer Auguste Mariette first breached these tunnels in the 1850s, he found them empty, their lids displaced and their contents, if there ever were any, long since vanished. Their true purpose remains an enigma, but their construction is a statement written in stone. The surfaces of these boxes are not merely smooth, they are flawlessly flat, polished to a mirror sheen that reflects the dim light with an almost liquid quality. Run your hand across them and you feel no deviation, no ripple or dip, just an unbroken plane of stone. This level of flatness is something we associate with modern machine shops and precision surface plates, not with ancient hand tools. But the real magic, the detail that truly baffles engineers, lies in the corners. Both the exterior and interior corners are perfect 90-degree angles, sharp and precise. Achieving a perfect external corner on granite is difficult enough, but an internal corner where two flat planes meet inside a solid block presents a physical impossibility for any tool that has a radius. Even our most advanced computer numerical control milling machines use cutters that are round, leaving a slight, measurable radius in internal corners. The boxes in the Serapeum have none. Their internal corners are as sharp as if the stone was carefully folded into shape rather than carved. This is a signature of a technology that operated on a different principle entirely. Precision engineers who have analyzed these boxes speak in terms of tolerances, the permissible limit of variation in a physical dimension. The flatness and squareness of these granite boxes exhibit tolerances that are within a few thousandths of an inch across their entire massive surface. To put that in perspective, that is a level of accuracy comparable to the parts used in aerospace engineering today. How do you achieve such a tolerance on a 70-ton block of granite without power tools, without even a reliable way to measure it? The challenge becomes even more pronounced when we examine the drill holes present in some of the boxes and their lids. These are not rough, conical depressions. They are clean, cylindrical bores, sometimes extending deep into the granite. The core samples that have been recovered from similar ancient Egyptian sites show a consistent, fine spiral groove. The rate of the drill's feed, the speed at which it advanced into the impossibly hard stone, is unnervingly steady and fast. It suggests a drill that did not slowly grind and abrade its way down, but one that sliced through the granite with immense, consistent force and astonishing efficiency. This kind of performance points to a tool that was both incredibly hard and under tremendous, stable pressure, a combination that simply does not fit the image of a worker using a bow-driven drill with a copper tip and abrasive sand. The machinery capable of such results would need a cutting head harder than granite, a massive and rigid framework to prevent vibration, and a power source capable of maintaining a constant, high torque. We have no evidence for such a device in the archaeological record of ancient Egypt. The Serapeum boxes, therefore, stand as a monumental argument against conventional explanations. They are not crude stone coffins, they are artifacts of hyper-precision. Their existence forces us to consider a process where the stone was somehow made compliant, allowing it to be shaped and polished to a microscopic degree of perfection. This is not the work of brute force, but of a knowledge so profound it could command the very structure of matter itself. What kind of mind could conceive of the geometry required to create such perfect forms, and what kind of hand could have executed it? The same language of impossible geometry is written across the sky. The Great Pyramid of Giza is not merely a pile of stones pointed north. It is aligned to true north with a deviation of just 3/60ths of a single degree. This is an accuracy that surpasses the alignment of the Royal Observatory in Greenwich, London, a building constructed with the full knowledge of modern astronomy and precision instruments. How could a civilization without the telescope or the compass achieve such a feat? This is not an isolated example. At Machu Picchu, structures are oriented with breathtaking precision to capture the sun's rays during the solstices. And at the Temple of Karnak in Egypt, the entire complex aligns so perfectly with the celestial movements that the rising sun on the summer solstice would illuminate the deepest, most sacred inner sanctuaries. These are not rough approximations. The alignments are accurate to fractions of a degree, a level of precision that implies a deep, sustained, and scientific observation of the heavens over countless generations. This celestial choreography required more than just stargazing. It demanded a sophisticated understanding of mathematics and geometry. Historians of science have long noted that the very dimensions of the Great Pyramid seem to encode fundamental mathematical constants. The ratio of its perimeter to its height is remarkably close to 2 times pi, the universal constant that defines the relationship between a circle's circumference and its diameter. Was this a deliberate act of encoding cosmic knowledge into stone, or is it a mere coincidence? The sheer repetition of such mathematical harmonies across different ancient sites suggests a conscious design, a shared blueprint based on a forgotten science. This mathematical foundation was not an abstract exercise, it was the absolute prerequisite for the stonework itself. You cannot build a structure aligned to a fraction of a degree with stones that are crudely shaped. The precision of the layout demanded an equal, if not greater, precision in construction. Every block had to be cut to an exact dimension and placed in an exact location. A single block cut just 1 degree out of square would throw the entire alignment of a wall off over a long distance, a cumulative error that would be glaringly obvious in the final structure. Yet, these errors are virtually non-existent. This points to a systematic use of a standard unit of measurement. In ancient Egypt, the royal cubit was not just a rough measurement based on a pharaoh's forearm. It was a precisely defined unit that was consistently used across thousands of years and hundreds of miles of construction. This standardization is the hallmark of an advanced, centralized, and systematic approach to engineering. The planning phase must have been as monumental as the construction itself. Before a single stone was quarried, master architects would have needed detailed plans, scaled drawings, and a profound understanding of geodesy, the science of measuring and understanding the Earth's geometric shape. They were not just building on a flat plane, they were building on the curved surface of a planet, and their alignments prove they accounted for this. This level of foresight and planning completely shatters the image of primitive slave labor. It reveals a civilization of surveyors, mathematicians, and astronomers who could visualize a project spanning decades and then execute it with machine-like accuracy. This mathematical mind, capable of such grand and precise designs, would not have relied on clumsy, inefficient methods to shape its primary material. The same intellect that could calculate the precession of the equinoxes and align a pyramid to true north would have surely possessed a technology for working stone that was equally refined and equally precise. Their architecture was a physical manifestation of their cosmology, a perfect marriage of earth and sky, and the very stones themselves had to obey this perfect mathematical order. Such a grand vision would never have been realized without a master plan. Before the first stone was ever touched, ancient architects were likely working with detailed blueprints and scaled models, coordinating a project of staggering complexity. We find clues to this in miniature stone sets discovered near some megalithic sites, small, perfectly carved replicas of the massive blocks that would eventually form the walls. These were not toys or ritual objects, but functional prototypes, three-dimensional maps that allowed the builders to test the fit and geometry of every unique piece before committing to the back-breaking labor of quarrying and moving the full-sized versions. Think of it as a gigantic stone jigsaw puzzle, solved in miniature first to ensure that when the 70-ton pieces arrived on site, they would lock together without a single error. This level of pre-planning speaks to a mind-boggling degree of foresight. Modern architects who study these sites point to the immense challenge of scaling up a design without introducing cumulative errors. A deviation of just 1 millimeter in a small model could translate into a gap of several centimeters in the final, colossal structure. Yet the evidence shows no such compounding mistakes. How did they manage this flawless translation from model to monument? The answer lies in a sophisticated toolkit of surveying and layout techniques that rival our own. They used precisely knotted chords for measurement, establishing consistent units of length that were used across vast distances. They employed sighting lines, aligning long poles or markers to create perfectly straight baselines across uneven terrain. For ensuring a level foundation, they used water levels, a simple yet brilliant technology where water in a trough finds its own level, providing a flawless horizontal reference point regardless of the ground's contour. These tools required not just skill, but a deep understanding of geometry and physics. Communicating these complex designs across generations of workers was another monumental task in itself. This was not a single lifetime's work. The master architect who drew the first lines in the sand would never see the capstone set in place. The plans had to be so clear, so systematic, that they could be understood and executed by master builders who inherited the project decades later. This suggests a formalized system of education where knowledge of sacred geometry, precise measurement, and construction techniques was passed down within a guild of skilled artisans. They were not mere laborers, they were the custodians of a sacred science. This glimpse into ancient project management reveals a civilization capable of breathtaking organization, a society that could mobilize and coordinate a highly specialized workforce for a singular, transcendent goal. Who were these workers, and what extraordinary skills did they possess to turn these perfect blueprints into stone reality? Behind the silent perfection of the stone lies a symphony of human coordination. A pyramid was not built by a faceless mob, but by a highly organized society of specialists, a civilization within a civilization. Archaeological estimates suggest a permanent workforce of tens of thousands, with numbers swelling during the annual inundation of the Nile when farming ceased. This was not slave labor, but a national project that employed a vast cross-section of society. The logistics are staggering to contemplate. Think of a modern mega-project like a dam or a skyscraper, with its engineers, crane operators, and welders. Now translate that into the ancient world. There were specialized teams of quarrymen who understood the hidden grain of the granite. There were the haulers, masters of leverage and friction who moved multi-ton blocks on sledges. There were the stone shapers, the true artists who possessed the secret knowledge of shaping. And there were the fitters, the final assemblers who ensured each block clicked into its preordained place with that legendary precision. Each role required a deep, specialized knowledge that could not be learned in a season. This knowledge was a precious commodity, passed down not in classrooms but through families or guilds. A father would teach his son the precise angle to strike a specific type of stone, or the secret recipe for a polishing compound. An anthropologist studying ancient social structures noted that such complex projects required a hierarchy of overseers, foremen who could read the master plans and translate the architect's grand vision into daily tasks for hundreds of teams. This was a seamless chain of command, from the divine king down to the apprentice learning to tie the correct knot. The training was a lifelong apprenticeship. A young boy entering the Stone Shapers Guild would spend years simply observing, then practicing on broken fragments, then perhaps assisting on an unimportant, hidden block, and only after decades would he be trusted to work on a critical, visible surface. This rigorous, generational system is the only way to explain the incredible consistency we see across centuries of construction. The sheer repetition of perfect angles and seamless joints across millions of stones is a testament to a standardized, ingrained skill set. These were not laborers, they were masters of their craft. Their hands were their micrometers, their eyes their levels. They were the human instruments of a grand design, driven by something far more powerful than a command. What profound belief could inspire such a monumental, multi-generational effort? For these master builders, perfection in stone was a spiritual imperative, not merely an engineering goal. They saw the world as a sacred text where every mountain, river, and star was part of a grand, harmonious order. To construct a temple or a pyramid was to participate in that cosmic balance, to create a microcosm of the universe itself. A single misaligned stone was not just a flaw, it was a spiritual offense, a crack in the fabric of reality that could disrupt the delicate harmony between the human world and the divine. This profound belief system transformed construction into a form of worship, a ritual where precision was the highest form of prayer. The stone itself was not an inert material to be dominated. In the Andes, the Inca understood stone as alive, possessing a spiritual essence they called kamak. A master builder did not simply cut a rock, he conversed with it. He studied its form, its grain, and its spirit, seeking to understand how it wished to be placed. The legendary polygonal walls of Cusco are a testament to this philosophy. Each uniquely shaped block was not forced into submission, but carefully fitted to its neighbors, allowing the entire structure to breathe and shift with the living earth during earthquakes. The goal was not to conquer nature, but to collaborate with it, creating a structure that was as resilient and alive as the mountain it was built upon. Similarly, in ancient Egypt, the drive for perfection was fueled by a quest for eternity. The pharaoh's soul needed a perfect vessel, a home for eternity that was as unchanging and orderly as the cosmos. The pyramids, aligned with pinpoint accuracy to the cardinal directions and the circumpolar stars, were not just tombs, they were resurrection machines designed to channel celestial power and ensure the king's eternal journey. The flawless, mirror-smooth surfaces of the granite sarcophagi were essential. Any imperfection, any crack or rough spot, was a potential trap for the soul, a flaw that could prevent its transformation and ascent to the stars. This spiritual context explains the otherwise inexplicable effort. Why spend generations achieving a surface flat to within 1/1000th of an inch on the inside of a box that would be sealed in darkness forever? Because in their worldview, the spiritual integrity of the vessel was everything. The physical perfection was a direct reflection of its metaphysical purity. A historian of religion might explain that for these cultures, the act of building was a reenactment of the creation of the world. The primordial chaos was tamed into order, and their temples were the ultimate expression of that order. This philosophical framework required a technology that could achieve this perfect order in physical form. The methods they used, whether sonic resonance, chemical softening, or something else entirely, were not just clever tricks. They were sacred sciences, deeply intertwined with their understanding of the universe. The loss of these techniques may not have been a simple matter of forgotten recipes or broken lineages. It might have been a spiritual collapse, when the belief system that gave these practices their meaning and purpose faded away. The knowledge itself may have become hollow, unsustainable, and eventually incomprehensible. The stones remain perfect and silent, as monuments to a time when humanity built not just for this world, but for the cosmos. The very perfection of their stonework may have contained the seeds of its own oblivion. How does a civilization misplace the knowledge to move mountains and soften granite? The answer lies not in a single cataclysm, but in a slow, creeping twilight of forgetting. When empires fragment and social order crumbles, the first casualties are often the most specialized and delicate forms of knowledge. Imagine a master builder, part of a small, revered guild that has orally passed down the sacred formulas for softening stone for generations. This is not knowledge written in a book that anyone can read. It is a living tradition, a dance of precise gestures and whispered words taught from elder to apprentice over a lifetime. If that lineage is broken by a plague, a famine, or a foreign invasion that scatters or enslaves the knowledgeable, the chain is severed forever. The techniques were likely held by a tiny, elite class of artisans. Their power and status depended on this secrecy, making the knowledge vulnerable. A single generation failed to find worthy students, and the art was gone. The Great Library of Alexandria stands as a potent symbol of this fragility, a vast repository of ancient wisdom consumed by fire, its scrolls turning to ash and taking untold secrets with them. Historians often note that technological civilizations are surprisingly brittle without widespread literacy and durable media. A society can reach incredible heights, but if its core knowledge is concentrated in the hands of a few and transmitted by word of mouth, it rests on a foundation of sand. Natural disasters played their part as well. A prolonged drought could force a population to abandon its sacred building sites and scatter in a desperate search for food, severing the connection to the quarries and the rituals of construction. The knowledge was not just a set of instructions, it was intertwined with a specific spiritual worldview. When that belief system was replaced by a new religion or a conquering culture, the old ways were often deliberately suppressed. The methods were labeled as pagan magic, their practitioners sidelined. Why would a new ruler, seeking to establish his own legacy, continue the traditions of a vanquished people? The stones remained, but the understanding of how to work them faded into legend, then into myth, and finally into silence. This profound loss underscores a haunting truth. Such technologies are not inevitable milestones of progress. They are rare flowers that can bloom in specific conditions and just as easily wither away. Our own civilization, for all its digital storage and global networks, is not immune to such forgetting. This realization forces an urgent and compelling question. If this knowledge once existed, can we, with our modern tools of science, hope to rediscover it? A modern laboratory hums with a very different kind of energy, where scientists and enthusiasts are trying to resurrect a technology lost to time. Dr. Moises Tapia, a geologist from Peru, has spent years experimenting with the legendary plant that the Inca chronicles claimed could soften stone. He has applied concentrated extracts from native plants to samples of andesite, the same volcanic rock used in the walls of Cusco. Under controlled conditions, he has observed a visible change, a darkening and a slight tackiness on the rock's surface, making it soft enough to be marked with a fingernail. This is a small-scale success, a proof of concept that a botanical agent can indeed alter hard stone. Yet, the challenge of scaling this effect up to a multi-ton block and then controlling the hardening process with perfect precision remains a monumental hurdle. The gap between marking a small sample and molding a 70-ton granite box is a chasm that modern chemistry has yet to cross. Similar experiments are underway with sound. Researchers in materials science have long used ultrasonic frequencies to affect the flow and solidification of metals. Applying this principle to stone, they have found that specific resonant frequencies can create standing waves that reduce friction and even cause granular materials to behave like liquids. But achieving this on a block of solid granite with its complex crystalline structure requires energy levels and control that are still beyond our practical reach. The question is not just one of power, but of finesse. How did ancient builders apply this energy with such surgical accuracy without the aid of digital oscillators or amplifiers? One dedicated amateur historian, Christopher Dunn, an engineer himself, took a more mechanical approach. He attempted to replicate the famous drill holes found in Egyptian granite using a bow-driven drill and a slurry of quartz abrasive. While he was able to create a hole, the process was agonizingly slow, and the resulting core sample did not match the uniformity and feed rate seen in ancient artifacts. The ancient drill cores show a consistent, deep groove that suggests the tool was biting into the stone with an efficiency that defies the abrasive method. Dunn's experiment, while valiant, ultimately highlighted the technological gap rather than closing it. These modern endeavors, from the chemical to the acoustic to the mechanical, all converge on the same frustrating truth. We can glimpse the edges of the possibility. We can achieve small, localized effects, but we cannot replicate the process on the grand, confident scale of the ancients. Our attempts feel like clumsy approximations next to their masterworks. The very failure of these experiments is, in its own way, a form of evidence. It tells us that the solution is not simply a matter of trying harder with the tools we already know. It points toward a synthesis of knowledge, a forgotten synergy between chemistry, acoustics, and perhaps even a subtle understanding of planetary energy that we are only beginning to suspect. If our best modern science can only scratch the surface of this mystery, what does that say about the civilization that perfected it? The stones are not just a puzzle from our past, they are a challenge to our future. The towers of Chanquillo stand like a stony calendar carved against the Peruvian sky, each one a silent sentinel marking the sun's journey with a precision that feels almost supernatural. This is the domain of archaeoastronomy, a field that deciphers how ancient cultures wove the movements of the cosmos into the very fabric of their stone constructions. It reveals a truth far more profound than simple stargazing. These celestial alignments demanded a level of architectural precision that is inseparable from the mystery of the stonework itself. A solstice marker is useless if the slit in the wall is even a fraction of a degree out of alignment. The sun's ray will miss its target, and the sacred event will pass unobserved. The flawless flatness of a granite surface, the perfect right angle of a corner, these were not mere aesthetic choices. They were functional necessities for a technology that used stone to capture light and shadow with the reliability of a modern instrument. One archaeoastronomer studying the Intihuatana stone at Machu Picchu described it as a crystalline dial frozen in time. its angles so exact that they still cast a shadowless pillar of light at the precise moment of the solar zenith. To achieve this, the builders needed more than just keen observation. They required a masterful control over their primary material. How did they plan for such perfection? Their tools were elegant in their simplicity, yet devastatingly effective. They used the horizon itself as a giant protractor, marking the rising and setting points of key stars over many generations to establish a fixed celestial map. They employed the plumb bob and the water level to ensure their constructions were perfectly vertical and horizontal, creating stable reference frames against the moving sky. The grand corridor of the Karnak temple, for instance, acts as a long, narrow telescope aimed at the rising sun on the winter solstice, for that single beam of light to travel unimpeded and illuminate the inner sanctum. Every single pillar and lintel along that path had to be placed with geometric exactness. This celestial connection points toward a holistic science, one that saw no separation between the study of the stars, the art of building, and the nature of the stone beneath their feet. It suggests a unified knowledge system where understanding the heavens meant also understanding how to command the earth. The master builders looked upon the earth not as an obstacle but as a partner. Their quarry sites were not chosen at random. They were selected with a geologist's eye for hidden advantage. They sought out the specific places where nature had already done half the work for them, exploiting the planet's own weaknesses to liberate the stone. A primary example lies in the granite quarries of Aswan, Egypt, where the famous unfinished obelisk remains attached to the living bedrock. The quarry floor is not a chaotic mess of rubble. It is a landscape of precise, linear trenches. These trenches follow the natural fracture lines in the granite, planes of weakness geologists call joints. The builders did not fight the stone's inherent structure, they listened to it. By inserting wooden wedges into these natural cracks and then soaking them with water, the wood would swell, exerting a steady, immense pressure that cleanly split the granite along a perfect, predetermined line. This same principle of thermal expansion was used with fire. By building controlled fires against a rock face and then rapidly cooling the heated stone with water, the thermal shock would cause the granite to spall and fracture along its crystalline boundaries. This was not brute force, it was a precise application of physics, a gentle persuasion that coaxed the stone from the earth. The evidence for this is etched into quarries worldwide. At Ollantaytambo in Peru, the andesite quarries high on a mountainside show clear signs of channeling, where deep, straight grooves were cut to isolate massive blocks. How was this achieved in such a hard stone? Geologists point to the mineralogy of the site itself. Often, these quarry zones are rich in deposits of softer minerals or are crisscrossed with veins of calcite or other soluble materials. Water, especially when slightly acidic from natural vegetation, would seep into these veins, slowly dissolving and weakening them over centuries. The builders, through generations of observation, learned to identify these softer zones. They would then direct their efforts there, using the water not just as a tool for splitting, but as a natural saw that did the work over time. This represents a profound, accumulated wisdom. It was an empirical science, built not in a laboratory but over millennia of living in intimate contact with the land. They learned which stones were easier to work after a rain, which quarry faces yielded better blocks in the morning sun versus the afternoon shade. This knowledge transformed their relationship with the material. The quarry was not a place of endless toil, but a library of stone, where every crack, every color variation, and every mineral inclusion told a story and offered a strategy. This pragmatic, deeply integrated approach reveals a civilization that saw the environment as a full of tools, if only one knew how to read the instructions. What incredible instruments of verification did they then use to ensure their liberated stone met such impossible standards? The master builder's final and most critical act was verification. He would take a granite straightedge, its own surface polished to a flawless plane, and lay it gently across the face of a newly shaped 70-ton block. Peering into the microscopic gap between the two stones, he looked for the faintest sliver of light. If even a single photon passed through, the block was rejected. This was not crude construction. It was quality control on a level that rivals modern manufacturing. The tools for such verification were as precise as the work they measured. We have found artifacts like the official cubit rods, carved from black granite and inscribed with minute subdivisions. These were not rough sticks. They were the national standard, the physical embodiment of a unit of length, kept in temples and used to calibrate the wooden and stone rulers used on site. A metrology historian studying these rods noted their incredible consistency, with the royal cubit varying by less than the thickness of a coin across centuries of use and across monuments separated by hundreds of miles. This was a system, not a suggestion. Ensuring perfect flatness required more than a straight edge. They mastered the use of surface plates, large, flat stones that were themselves reference planes. A craftsman could dust a finished block with red ochre powder and then press it against the master surface plate. Any high spots on the block would be revealed by the transferred pigment, guiding the final, delicate polishing. For perfect perpendicularity, they used set squares but not simple wooden ones. They employed the 3-4-5 triangle principle, a cornerstone of geometry, using knotted cords to create a perfect right angle every time. A rope marked in 12 equal segments could be stretched into a triangle with sides of 3, 4, and 5 units, guaranteeing a square corner for laying out foundations or checking the internal angles of a stone box. The most brilliant tool, however, may have been the simplest, the water level. A shallow trough filled with water provided a perfectly horizontal reference line that was immune to the uneven ground, allowing builders to ensure that courses of masonry were level across vast distances. They even used the sky itself as a tool. The precise alignment of a wall could be checked by observing the shadow cast by a tall, slender gnomon, verifying its orientation to the cardinal directions with celestial accuracy. This obsessive focus on measurement and verification reveals a culture that operated with a systematic, almost industrial mindset. The perfection of the stonework was not accidental or artistic. It was a mandatory outcome of a rigorous process. This systematic nature forces a profound historical implication. We are not looking at the slow, trial-and-error ascent of primitive technology. We are witnessing the mature application of a refined and deeply established science. The evidence of their metrology is as etched into history as their monuments are etched into the landscape, and it challenges us to completely rethink the narrative of human progress. These silent stones force us to rewrite the story of humanity itself. Our modern world is built upon a comforting narrative of linear progress, a steady climb from primitive beginnings to our current technological peak. Yet the evidence of atomic-level stonework shatters this timeline. It suggests not a straight line, but a great cycle, a rhythm of civilizations rising to breathtaking heights, only to collapse and vanish, leaving behind only their most durable monuments as cryptic clues. A philosopher of history once noted that we measure the past by the rubble we find. But what if the most advanced technologies leave no rubble, only perfected stone that we mistake for primitive merely because it is old? This paradigm shift forces a humbling question about our own place in history. We pride ourselves on our silicon chips and space telescopes, But could we, today, replicate the 70-ton granite boxes of the Serapeum with the same flawless precision, without our power grids and computer-controlled machinery? The answer is a sobering no. This realization redefines human potential. It suggests that intelligence and ingenuity are not modern inventions, but constants, capable of manifesting in radically different forms. The builders of these sites were not our primitive ancestors. They were our intellectual equals, perhaps even our superiors in their mastery of material science and natural energy. The implications ripple across academic disciplines. For archaeology, it demands a new humility, a willingness to let the physical evidence speak louder than entrenched theories. It calls for a collaboration with materials scientists and engineers who can read the language of tool marks and atomic structures that historians might miss. For engineering, these sites are not relics, they are textbooks. The seismic resilience of Inca polygonal walls offers masterclasses in earthquake-proof design that we are only now beginning to appreciate. The celestial alignments demonstrate a long-term astronomical accuracy that challenges our own rushed methodologies. Perhaps the most profound implication is the possibility of a common, forgotten source. How do we explain the same impossible precision appearing in the Andes, in Egypt, and in distant Japan? The conventional explanation of independent invention strains credibility. It is like two isolated cultures independently inventing the microchip without any contact. The geometric principles, the material choices, the obsession with celestial harmony, these are not just similar ideas, they are the fingerprints of a shared technological language. This points to a sophisticated, global culture in deep antiquity, or at the very least, a pervasive body of knowledge that flowed across oceans and mountains in a forgotten age of exploration. This is not about finding a lost continent, but about recognizing a lost chapter of human collaboration and discovery. Ultimately, this changes our identity. We are not the first to strive for greatness. We are the inheritors of a deep and mysterious past, living in a world dotted with the echoes of a grandeur we can barely comprehend. These stones are a gift and a challenge. They ask us to look at our own civilization and wonder what we are building that will last 10,000 years, and what fragile knowledge we might ourselves leave behind for some future people to puzzle over. Our modern world is built on concrete and steel, yet these ancient walls of perfectly fitted stone have outlasted empires. They offer a blueprint for a more resilient and sustainable future, one that works in harmony with the planet rather than fighting against it. The core principle is dry stone construction, a method that uses gravity and precision instead of chemical binders. Modern buildings rely on rigid materials like concrete, which is incredibly resource-intensive to produce and forms a brittle, monolithic structure. When the ground shakes, that rigidity becomes a fatal weakness, but the polygonal walls of Cusco demonstrate a different philosophy. Each irregular block is an individual component, free to shift and settle minutely during an earthquake. The entire structure dances, dissipating the seismic energy and then settling back into place unharmed. This is not just an ancient curiosity, it is a masterclass in seismic engineering that we are only now beginning to fully appreciate. Sustainable architects are now looking seriously at reviving these methods. They see the potential for modern buildings that use precisely shaped, interlocking stone or even recycled concrete blocks, assembled without mortar. This would drastically reduce the carbon footprint of construction, eliminating the need for cement production, which is one of the largest industrial sources of carbon dioxide emissions globally. The energy efficiency is inherent in the material itself. A thick stone wall, properly fitted, provides massive thermal mass, naturally regulating a building's temperature by absorbing heat during the day and releasing it slowly at night, reducing the need for mechanical heating and cooling. The techniques themselves are ripe for revival. The ancient understanding of a stone's natural cleavage plane could be enhanced with modern sonic imaging, allowing quarries to split blocks with pinpoint accuracy and minimal waste. The concept of chemical softening, even if only partially replicated, could revolutionize how we shape and recycle hard materials. Imagine a future construction site where stone is not cut with noisy, dusty saws, but is gently molded into form with botanical solutions, creating zero waste. The durability of these structures is their ultimate testament to sustainability. While a modern concrete building has a lifespan of perhaps a century before major renovation, these dry stone walls have endured for thousands of years with no maintenance. They are not just buildings, they are legacies. This is knowledge that transcends time, proving that the most advanced solution is not always the most complex one, but often the most intelligent and harmonious. Of course, such a radical rethinking of our building traditions does not come without its critics, and their voices form a crucial part of this ongoing mystery. A conventional archaeologist stands before a perfectly fitted Inca wall, a simple stone hammer in hand. The argument is straightforward and, on the surface, deeply compelling. We have found the tools, they say. We have the quarries littered with stone hammers. We have the experimental archaeology that proves, given enough time and human effort, these stones can be shaped. The absence of evidence for advanced technology, they argue, is itself evidence that it did not exist. This is the principle of Occam's razor, the idea that the simplest solution, the one requiring the fewest assumptions, is usually the correct one. A skeptic might ask, why invent a lost, high-tech civilization when we can explain the work with the copper and stone tools we have actually discovered? The sheer scale of labor is not an insurmountable barrier. With a large enough, well-organized workforce operating over generations, even the most monumental tasks become possible. The mainstream view is one of immense human ingenuity and patience, not forgotten science. A quote from a prominent Egyptologist captures this sentiment perfectly, stating that we must be careful not to underestimate the power of persistent, skilled labor. They argue that the ancient Egyptians were master craftsmen, not alien visitors or the heirs to a lost super-civilization. Their achievements were extraordinary, but they were human, and their methods, while sophisticated, were ultimately within our understanding. This perspective urges caution, warning against replacing one mystery with an even bigger one. The polished surfaces, that is the result of endless hours of grinding with sand and water. The precise corners, the work of meticulous stonemasons using simple measuring cords and stone abrasives. The lack of tool marks simply the sign of a final, thorough polishing that erased all traces of the initial work. It is a clean, logical, and evidence-based narrative, so why does it feel for so many like an incomplete answer? Proponents of more advanced theories respond not by dismissing these points, but by reframing them. They agree that skilled labor is essential, but they ask if it is truly sufficient. They challenge the very definition of a simple explanation. Is it simpler to believe that thousands of workers spent generations grinding down granite with sand, a process that would have created mountains of quartz dust and required an unimaginable supply of abrasives for which we find little evidence? Or is it simpler to propose that they possessed a more efficient, now lost method? The response is not to invoke magic, but to point to the physical anomalies that the conventional model cannot comfortably resolve. How does a copper tool with a hardness of 3 meaningfully shape quartz with a hardness of 7? It is not a matter of patience, it is a fundamental law of physics, like trying to use a stick of butter to carve a steel beam. The proponents turn the principle of Occam's razor back on the skeptics. They argue that the simplest explanation is the one that best fits all of the observed evidence, and the conventional tools simply do not account for the vitrified stone, the ultrasonic drill marks, or the perfect internal corners of the Serapeum boxes. These are not minor quibbles, they are fundamental contradictions in the data. The call, then, is for more interdisciplinary research, a collaboration between archaeologists, materials scientists, and engineers. They are not asking for a blind acceptance of radical ideas, but for a rigorous, open-minded investigation that treats these ancient sites as the complex engineering puzzles they truly are. This is not a debate between fact and fantasy, but a conflict between two different interpretations of the same silent testimony in stone. The resolution may not lie in choosing one side entirely, but in finding a new synthesis, one that acknowledges both the power of human labor and the possibility of a lost science that made that labor infinitely more effective. The stones do not take sides, they simply await a better question. These silent stones from Peru to Egypt speak a language of impossible precision, a testament to a forgotten chapter in the human story. We have walked through the evidence, from the geological defiance of granite to the mathematical minds that encoded celestial harmony into their blueprints. We have listened to the theories, from resonant sound and earth energies to the alchemy of plant-based chemistry. Each perspective offers a piece of the puzzle, yet the complete picture remains just beyond our grasp, challenging the very timeline of human progress. This mystery does not ask for blind belief, but for a courageous curiosity. It invites us to look at the world with fresh eyes, to question the narratives we have been taught, and to consider that the past holds secrets far more profound than we ever imagined. The answers may not be hidden in some lost library, but are waiting for us in plain sight, etched into the very stones we walk past. These ancient monuments are more than ruins, they are a conversation across time, urging us to remember the heights we are capable of reaching. What other wonders lie buried in our history, waiting only for us to ask the right questions? Share your own thoughts on these enduring mysteries in the comments, and join us as we continue to explore the deepest unknowns of our world.